Okay, let's hope this works. All right. So the next concept is what we call solubility product as an equilibrium constant. But before we define that, let me back up because we need to refresh our memory about what it means to be saturated. Do you guys remember when we when we had a solid that we were trying to dissolve? If you see solid present after you've stirred and stirred and stirred and stirred and you still see solid present, that means the solution is saturated. Right? Remember, saturated means you can't dissolve anymore. So what that means is for every one of these solute particles that dissolves and becomes aqueous, at the same rate, one of those solid particles rejoins the solid. So if these two processes are occurring at the same rate, this is at equilibrium. So for any dissolving process, we have to write a dissolving equation. So I'm just going to write one. CaCO3. This is called calcium carbonate. It's actually limestone. It's what like shells are made out of. So calcium carbonate, when it dissolves, it produces these two ions. When this reaction is at equilibrium, that means the rate of dissolving equals the rate of precipitation. And so if I had a sample of calcium carbonate in this beaker and I stirred, and the size of the solid stayed the same, I know that it's a saturated solution and I know it's at equilibrium. So what I need you guys to realize is that these two terms, right, they're related. If it's saturated, it is at equilibrium. Okay? All right, so because it's an equilibrium process, all equilibrium reactions follow the same rules, right? Rules like take the products over the reactants to get an equilibrium expression. Coefficients become exponents. Those rules. All the rules we talked about this unit, they all still apply here. So if I wrote the KSP expression for this reaction, it would look like this. But here's the problem. This is a solid. Calcium carbonate is a solid, right? And you know that solids cannot be expressed in an equilibrium expression. So therefore, the equilibrium expression now becomes this. And the term is no longer KEQ, it's called KSP. SP stands for solubility product. It is still a constant, but it's more specific now. They're saying that this applies to dissolving. It only applies to dissolving equations, KSP. Okay, so given a compound, can you write a dissolving equation? Well, if you know the formula and you know the charges, you should be able to. Barium chromate, this is the formula for barium chromate. Barium is a +2 charge, chromate is a -2 charge. So a dissolving equation would simply look like this. Make sense? Now, you'll often see aqueous written after here, and if I wasn't a little bit lazy, then I would be writing AQ after everything. But you don't have to write AQ. Why? It's inferred, right, because the charges are given, right? Ions are aqueous. That's kind of assumed. Silver phosphate. The formula for silver phosphate is Ag3PO4. So the dissolving equation, you have to pay attention to the subscripts. This 3 here means that we will get 3 silver ions and a phosphate ion with a charge of -3. And I also want to bring up something that I've seen people do. Here's another example. CaI2. Right here, this subscript of 2. There are no diatomic ions. So what you have to realize is that the 2, it's not I2, it's 2 iodine ions. And the reason is because calcium ions are not diatomic. One is on this side, one is on this side. If these 2 were to be pulled apart and go into water, are they connected to each other? No. So therefore, why would you write I2, right? 2 I's, right? There are 2 of them. They're separate. All right. So if you're okay with writing the dissolving equation, the next thing is to write what's called the KSP expression. And writing the KSP expression is exactly what you have always done, except that you don't include the solids. So the KSP expression for this reaction would be the concentration of the products multiplied by each other over 1, because you can't write the solid. But you don't even have to write the 1. For the silver phosphate, silver is going to be cubed because of this guy, right? Coefficient of 3 means you raise it to the 3rd power. You guys okay writing dissolving equation and then writing a KSP expression? Okay. All right, so let's get into the nitty-gritty. Finding the KSP value if given the solubility. All right, so when they say solubility, recall that solubility means the maximum amount that can be dissolved. All right, that's the maximum concentration that can be dissolved. So here they are telling us we have a solution of silver bromide, and they're telling us the molarity. That molarity is the solubility. So these problems that I'm showing you today always start with the same 2 steps. Write an equation, write an expression. And that's what we're going to do. AgBr dissolves to form silver ions and bromide ions. Okay. The expression, KSP is equal to the concentration of silver times the concentration of bromide. Again, we are ignoring the solid. Alan, question?
Just to make sure, the silver and bromide, those are aqueous, right? They're
Correct. Yep. Yeah, they're aqueous ions, right? Okay. So now that I have an equation, if I want to solve for the KSP value, I have the formula to do so, right? This is a 3-variable equation. I just need the silver and I need the bromide concentrations, and that will help me find the KSP. So I need to find out what the concentrations are. So I start with what they gave me. All right, so here, 7.1 times 10 to the negative 7 molar AgBr. Well, in every AgBr, there is 1 silver. So therefore, the molarity of silver is the same. Now, it might look like that it didn't really do anything. The reason why I wrote that out is to show that if I know the concentration of the compound, I know the concentration of the ion. I'm going to do that again, but this time I'm going to do it for bromide. And it's not always going to be 1-to-1, by the way. Right? You could have like AgBr2 or something. All right. We now have the concentration of both ions. So now we can plug them into our equation, our expression, and we could solve for the actual value of KSP. Which will be 5.0 times 10 to the negative 13. All right, let's review what we did here. We were given the solubility, which is a molarity. We had to first figure out what the concentration of the ions were, and then we wrote an expression so that we could substitute the concentrations into the expression to find KSP. So these problems come in two varieties. This one, the one we just did here, where we're trying to find KSP, and the second variety is finding the solubility if you know KSP. But you know what? The steps start the same. They always start the same. Write a dissolving equation. So PbCl2 solid will form lead ions and 2 chloride ions. Kira.
Can we go over how to put it into our calculator?
Oh, this guy? So you're literally taking, so it's the KSP for this one was 7.1, and I use the exponent key, you know, that the second comma. And it's the same number, so we actually could just square this one. (7.1) second comma -7, hit enter, and then hit square, and then hit enter. Are you getting it?
Yeah.
If not, show me your calculator. I could see what you're doing. The important thing is make sure that your negative sign is the negative sign, not the subtract function.
Okay.
And it's second comma for your E, not alpha E.
Okay.
Okay. All right, so writing a KSP expression for this. Lead ion times chloride ion squared. All right. So here they give us the KSP, right? This time this is given. So we need to figure out what the concentrations are, and that's what's going to tell us what the solubility is. All right. So first, it's helpful to write a little ice table. Just going to duplicate this, make a copy of it, so I can make a little table underneath it. And the reason why I say it's useful to do an ice table is because it points out the fact that one of these will be x and this other one will be 2x. And you might say, oh, well, why is that important? It's so that you substitute in the correct variable. Because the KSP will be quantity x times quantity 2x quantity squared. And since the KSP is known, 1.7 times 10 to the minus fifth is equal to, this all here will amount to be 4x cubed. You don't really need solver. I mean, you could use solver, it's fine, but you don't need it. We're just dividing both sides by 4 and then taking the cubed root. And so x, we get 0.0162 molar. X is the solubility. That is the maximum concentration that I can dissolve of lead chloride. 0.0162 moles in every 1 liter. Right? That's not very soluble. 0.0162 moles, that would be like a gram in 1 liter. Yeah, question.
How did you get the equation 1.7 times 10 to the negative?
Oh, that was given in the top.
How did you get the other part? 4x cubed.
Oh, well, what's 2x squared? 2 squared is 4, right? X squared is x squared times x, so 4x cubed. Yeah. Yes?
In the table, why is the column of the different compounds?
Oh, okay, yeah. In your ice table, solids and liquids do not have measurable concentrations.
Yeah.
Yeah.
And how do we know that we're going to zeros without flattening?
Oh, because you weren't told what the initial concentration was. You were trying to dissolve it, so there was nothing there at the beginning.
Perfect, thank you.
Okay. Good questions. Okay. I'm going to add a page here because I want to make sure we know how to do this before we do the last thing. So what I'm going to do is I'm going to give you some more examples of both of those problem types. All right. So first, I'm going to make up a problem because I don't have solubilities all memorized in my head. So let's say that I don't know what that is, the solubility of compound QX2 is 0.015 molar. Find the KSP value. Okay, guys, remember what I said. What are the first 2 steps that we always do in these types of problems? Write a dissolving equation. Okay, so QX2 would separate into these ions. Okay. What else do I need? The expression, okay. KSP is the concentration of Q times the concentration of X. That will be squared. Okay, so in order to find KSP, I need to find those concentrations. So let's start with the concentration that they gave me, 0.15 molar QX2. In every 1 QX2, how many Q's are there? 1. Whoops, that's a 0.015. 0.015. All right, I have my concentration of Q. Let's do this again. 0.015 molar QX2. And every 1 QX2, how many X's are there? 2. And solve. So, if you are given the solubility of a compound, this is how you find the KSP. The general steps are going to be the same, but you have to pay attention to the details, because what if your coefficients are different, right? If the coefficients are different, then you're substituting different values, right? And you have different, numbers of ions per formula. So you have to pay attention to that kind of stuff. So that was me walking you through one. Let me give you one for you to do completely on your own. Got this new made-up formula called RZ3. Sounds like something out of a Star Wars spinoff. So, did anybody get a value? It's a pretty small value.
I got 1.555 times 10 to the
Negative what?
-8.
You're right in the right direction. We're a little off. I got a smaller value than that, actually, by like a factor of 3.
I got 5.6 times 10 to negative 11 power.
Yes. Okay, so let's go through that. All right, so I got to figure out what to put in these brackets. I know there's 0.0012 molar RZ3. And so for every RZ3, there is 1 R. Okay, so this concentration is still 0.0012. But it's the Z. See, for every RZ3, there's going to be 3 Z's, right? Which is 0.0036. And so that's our value that we plug in, and that has to be cubed. So after punching those numbers in, 5.6 times 10 to the negative 11 is the KSP value. Okay, that is how you find the KSP value. Let's do a couple where you have to find the solubility. All right, so the KSP for calcium fluoride is 4.2 times 10 to the minus 4. Find the solubility. The steps are the same to start. You need an equation, you need an expression, but this time you're solving for x. All right, guys, what do we think? What kind of value for x did we get?
0.047.
Yeah, good. 0.047. Okay, so how did we get that? Well, according to our ice table, the concentration of calcium would be X. So that's what we substitute there. The concentration for fluoride would be 2X, so that's what goes in there. And so essentially you have the KSP equals X times quantity 2X squared. Solve for X. How are we doing? Good? Okay, so you guys, are you seeing the math rules don't change? How we do equilibrium problems is still really all the same. You have to set up an expression. The coefficients become exponents, right? And your ice table helps you figure out what you plug in. Okay, so then, the last thing we're going to talk about today is determination of whether a precipitate forms. And what this means is we're solving for Q again. Remember, Q is used for initial concentrations, not equilibrium. So the tricky thing about this, it's not really tricky, but the thing you have to take your time with is you really need to make sure that you get your concentrations set up right. So let's just jump right in, and then I'll explain the process as we do this. In this problem here, in this example problem right here, they are telling us there's a concentration of chromate and a concentration of silver. What they're doing is they're adding these two ions together, and they're asking, will it precipitate form? So how you start the problem is always the same. You still have to write a dissolving equation. In this case, the dissolving equation is going to be for silver chromate. And the expression is going to be silver squared times chromate. Okay, so I don't have, you know what? I made a mistake here. I just totally made a mistake against what I said. This is not at equilibrium. These concentrations they are giving me are the initial, so I'm actually solving for Q. So if I plug in the values, I get 1 times 10 to the minus 9. And just for a refresher, the KSP for this reaction was given earlier. I think it was 2 times 10 to the negative. It was somewhere earlier here. Wasn't it? Silver chromate, silver chromate. Where's silver chromate? Oh, here. Duh. It's right here. Okay, silver chromate is given. How does Q compare to K? How does it compare? It's bigger. Q is greater than KSP. And whenever Q is greater than the equilibrium constant, that means you have too much product. That means the reaction must go backwards. Going backwards for a dissolving equation means we start to see this. What did I just highlight? Solids. If this reaction, if a dissolving equation goes backwards, we see solids, meaning we see precipitation, because precipitation means solids. And visibly, you can tell because it'll start to get cloudy, and then you'll start seeing chunks. So, everything we've just done here in this problem is the same type of concepts that we used when we worked with Q earlier in the unit. So, now let's talk about a problem where you have to manually figure out the concentrations before you plug them into Q. because here they just gave us the concentrations. So imagine this situation here, okay? We are mixing this volume of this molarity of potassium chromate with this volume of this molarity of silver nitrate. If I'm mixing potassium chromate and silver nitrate solutions together, you guys understand that these are double replacement reactions, and to figure out what the precipitate's going to be, it helps to understand the solubility rules, right? Potassium will end up going with nitrate, and silver will end up going with chromate. Oh, it's silver chromate again. So Ag2CrO4 is the likely precipitate. All right, so my equation looks just like the one we did. Actually, it's the same one we did. Okay, there is our equation. It says calculate the molarities of ions involved. What ions do I need to know? I need to know the silver, I need to know the chromate. I don't need to know the potassium, and I don't need to know the nitrate because those are spectator ions. They are not responsible for forming a solid. So, how do I do that? Well, this is how. Remember how molarity times volume gives you moles? I take the volume in liters and multiply it by the molarity that's given. And this will give me moles. That's moles of potassium chromate, but it's not potassium. I don't need potassium, so I need to convert out of potassium chromate and get into just chromate. Okay, so I have the moles. Well, how do you find molarity? It's what over what? Moles over liters. I am mixing two test tubes together. All right, I'm putting them both into like a larger test tube. This contains 50 milliliters. This contains 50 milliliters. What's my total volume going to be? 100 milliliters once they're mixed, right? So in liters, it's 0.1 liter, right? So I need to take my moles and divide it by the 0.1 liter, and that will give me the molarity of the chromate, which will be 3.4 times 10 to the minus 4 molar. Question, yes?
Can you explain what you did with that equation?
Which equation?
That whole equation I'm lost.
The silver chromate solid?
Yeah.
Well, that's just the dissolving equation. I figured out what the dissolving equation was because I remember that nitrate and potassium are soluble.
Yeah.
And
I get that, but I mean the second one. The one that you just did.
Oh, okay. So here what I'm doing is first I'm finding moles. Right? So if molarity is moles over liters, liters times molarity is how we find moles.
So why are you trying to do it for chromate?
Because what's the KSP expression going to be? Or I should say Q, because these are not in it. Q will be this. I need the initial concentration of chromate.
Yeah.
So the goal is to find the concentration of chromate.
What about for silver?
I haven't done it yet.
Okay.
So now let's do it for silver. Okay, so 0.05 liters times 9.6 times 10 to the minus 5 molar silver nitrate. Does everyone see where I'm getting those numbers from?
Yeah.
All right. So this is 4.8 times 10 to the minus 6 moles of AgNO3. Nitrate we don't need. I just need the silver, so I have converted out of that. And both ions, they're in the same solution, right? So the total volume is the same. So I need to divide this again by the total volume, which is 0.1 liter. So 4.8 times 10 to the minus 5th molar silver. Yes?
Why does silver have a subscript of 1 and not 2?
It's silver nitrate, because silver is a +1, nitrate is a -1. So the source of my silver was silver nitrate. The source of my chromate was potassium chromate. These two are going to be mixed together, and once they mix together, now is when I am concerned with plugging them in here. Okay, so to finish the question, Q will be the concentration of silver, which will be squared, times the concentration of chromate, so let's see what we get. (7.8 10 to the negative 13). Remember that the KSP for this compound was 2 times 10 to the negative 12. Right, it was up here from the previous problem. What's going to happen? I've mixed these two test tubes together. I've mixed this potassium chromate with this silver nitrate, shaken it up. We have to recalculate the concentrations of the ions and then solve for Q. The value of Q is 7.8 times 10 to the negative 13. What does that mean? Will this precipitate and go backwards, or will it stay clear and go forwards? Yes. The Q value is smaller than KSP. Remember, when Q is too low, that means you don't have enough product. That means reaction will go forward. In the dissolving equation, going forward means staying aqueous.
Where is the KSP?
Here.
Oh.
So this is, there's a more work involved to find the concentrations. But in essence, the heart of the question is just a comparison of Q to K. Most of the work is done in calculating what the concentrations will be before you plug them into Q. Conceptually, though, it's kind of, we've been following the same themes. All right. I'm guessing we have time. We'll do one more just to make sure, to help you guys feel better about this. We're not going to cover the next topic, but I'm going to add another page here just so there's more room. Okay. I think I used, what was it? Barium fluoride earlier? Where did calcium fluoride? 4.2 negative 4. Okay. KSP for calcium fluoride. 4.2 times 10 to the minus 4. Okay, so here's what we're going to do. We mix 20 milliliters of 0.01 molar calcium nitrate with 30 milliliters of 0.005 molar sodium fluoride. will a precipitate form? Okay, so this is what I am dealing with. I'm going to write my equation. The Q expression will look like this. Oops. All right. Find molarities. So for calcium, you got to figure out moles. And this is why we multiply the volumes by the molarity. So 0.020 liters times 0.01 molar is 0.0002 moles of calcium nitrate. It's just calcium that we need, so let's get rid of the calcium nitrate. What is our total volume?
$50.
50 milliliters, which in liters is 0.05. So our molarity is 0.004 for calcium. For our fluoride, 0.03 liters times 0.005 molar .00015 moles of sodium fluoride. In every sodium fluoride, there is one fluoride, so 0.00015 moles of fluoride divided by the same volume, .003 molar F minus. Solve for Q. Tell me what you think. That's right. So, will we see a precipitate? Is this reaction going to the right or is it going to the left? It's going to the right. Because Q is less than K, there's not enough product, and the product is the dissolved state. So if it goes to the right, everything we see is aqueous, no solids. Yes, Alan?
When do we determine the KSP?
It was given. The KSP would have to be given to you in this problem. I gave it to us,
Oh, okay.
yeah, earlier.
4.3 times 10 to the -4?
Yeah. So, what is the point of this? What is the application of KSP? Well, does anybody want to become a pharmacist or a doctor? You want to prescribe certain medications? You want to inject something intravenously into someone's veins? You cannot have it solidify. What would happen if things solidify in your bloodstream? Blockages, aneurysms, heart attacks, all sorts of bad things, right? So there's a reason why chemistry is a required part of a pre-med curriculum, okay? All right, that was a lot. I'm going to stop the recording here.